You might say that the introduction to high vacuum goes back in time to two 17th century physicists whose accomplishments are known to every schoolboy. Torricelli, who in discovering the principle of the barometer created a vacuum in the top of the tube of mercury, and von Guericke, the first experimenter with vacuum and maker of the first vacuum pumps. With one of them, he evacuated the air from a pair of copper hemispheres and staged that dramatic 16-horse demonstration to prove that the atmosphere exerts pressure. We know how much thanks to Torricelli. We also have a standard. The height of a column of mercury in millimeters is the international basis for measuring atmospheric pressure. And in honor of Torricelli, 1 millimeter of mercury is now known as 1 torr. 760 torr, or millimeters of mercury, constitute 1 standard atmosphere. The height of a column of mercury the atmosphere will support at 0 degrees centigrade, at 45 degrees latitude, and at sea level. Vacuum starts at sea level. For the higher you go, the higher the vacuum, or the lower the pressure. At sea level, as we know, it is 760 torr. 100 miles up, it is only 1/100,000th of a torr. At 300 miles, it's only 1/1000th, which is about the limit of vacuums we can produce with our present-day pumps. It's more convenient to define a rarefied condition in terms of particle density, which at this level is about 10 million particles, gas or air molecules, per cubic centimeter of space. That's about 1/millionth of a millionth of the density at sea level. Scarcity of air particles is a necessity in atom smashers. In this 30 billion electron-volt synchrotron, the vacuum chamber is a circle 1/2 mile in circumference. Protons injected into the vacuum chamber travel 150,000 miles around the circular path without colliding with a single molecule of air. The particles begin their trip in an evacuated tube in this linear injector. The pressure in the tube is held down to about 2/millionths of a torr. That's 2 times 10 to the minus 6th power. Today's space simulator chambers are relying on high vacuum techniques for results. Components of entire systems can be tested in the laboratory before committing them to the ionosphere. In this, as in all high vacuum applications, there is a dual problem: producing the vacuum and measuring it. The most common device for producing low pressures is the mechanical oil-sealed rotary pump. It is available in a variety of sizes, from small portable types, such as the one on the dolly in the foreground, to heavy-duty types, such as those installed here, serving the Cosmotron particle accelerator. Rotary pump capacities range from several hundred cubic feet per minute down to 1 cubic foot per minute. The rotary-type pump consists of a stator case with an intake port, an outlet port and valve, and a cylinder mounted eccentrically within the stator. It is equipped with spring-loaded vanes that make a seal with the stator, aided by an oil film. Air is swept around the chamber and is compressed as it reaches the outlet port. The leakage between the outlet valve at atmospheric pressure and the inlet space at vacuum limits the pressures that can be reached by these pumps. Another limitation is the vapor pressure of the oil used to seal the flow of air between the various parts. The Roots type pump eliminates the oil seal problem and is capable of a somewhat higher vacuum. Of the two Roots pumps in this installation, the smaller one handles 1,600 cubic feet per minute. The larger, 5,000 cubic feet. The figure-8 lobes are characteristic of the Roots type pump. They rotate with an action similar to that of the gear type pump used in gasoline engines. A tight seal between the lobes and the casing is made by the closely machined parts. This type of pump cannot discharge directly to the atmosphere. It requires a rotary mechanical pump at the exhaust port. Pressures of 10 to the minus 5 millimeters of mercury are readily attainable with the Roots type pump. If we could see the flow of air molecules in a chamber pumped by a mechanical pump, we'd notice that they collide with each other a great many times before hitting the walls. This condition is called viscous flow. As the molecules are removed, those that remain collide with each other less frequently, and they soon have a very long, mean-free path, as it is called, between collisions. This condition is known as molecular flow. The molecules wander about aimlessly with no particular urging toward the pump orifice. Thus, the pump can capture only those particles that happen to be in its area. Obviously, some other method of pumping must be used at these low pressure levels. The workhorse of the high vacuum pump family is the diffusion type. Pumps of this type are made of metal and of glass in sizes ranging from 1 or 2 liters per second up to 40,000 liters per second. A diffusion pump has no moving mechanical parts. Operation is therefore highly reliable. The heart of the pump is a nozzle assembly that operates on a simple principle. The basic elements of the pump are a cylindrical water-cooled casing, the jet assembly, a reservoir of oil, and a means of heating the oil. Oil vapor is directed downward in jet form by nozzle caps. The ejection is at considerable velocity, and the rushing vapor collides with any air molecules in the vicinity. Repeated collisions impart downward momentum to the air molecules, and they are eventually concentrated in the general region of the outlet, called the foreline. At this point, a rotary mechanical pump will evacuate the air molecules and discharge them to the atmosphere. When the oil strikes the water-cooled casing, it condenses and flows back into the reservoir and is reboiled. Most modern pumps have multiple jets that separate the oil into high and low boiling point fractions, which aids in obtaining a high vacuum. Although oil is most commonly used as the working fluid, some diffusion pumps work with mercury. In order to prevent migration of the working fluid particles, traps or baffles are mounted above the diffusion pump. The baffles intercept the straight-line paths of oil or mercury molecules and also prevent passage of molecules that have collided with the walls and changed direction. Baffles are ordinarily cooled by refrigerant lines to keep the surface temperatures in the range of minus 40 to minus 180 degrees centigrade. Baffles take various forms. Some are cone-shaped, and some have chevron-shaped vanes. But all of them have the same function, to prevent oil migration from the pump to the chamber. Baffles are not needed in this type of vacuum pump since there is no working fluid or vapor. It is known as a getter ion type. The action is based on the phenomenon that a fresh, clean metallic surface will combine chemically with most of the common gases and vapors. In the getter ion pump, titanium is frequently used as the active metal. Barium, molybdenum, and tungsten have also proven successful. In the evaporating type of getter ion pump, cathode bombardment causes the titanium to evaporate. Here we see one such atom as it travels toward the cooled wall, where it combines with a gas molecule. Oxides, nitrides, and hydrides, and other more complex combinations result in stable compounds, thus removing the gases from the pump chamber, as well as from any chamber or volume connected to it. In the getter ion pump, the noble gases, such as helium and argon, are pumped electronically. Electrons passing through a wire basket triode ionize these gases, which are then accelerated into the pump walls. Pressures below 10 to the -9 torr can be reached if the pump walls are outgassed by baking and then cooling while the pump is in use. A different technique is used in another version of getter ion pump. In principle, an electron emitted by high voltage discharge travels in a long spiral path under the action of a magnetic field. The electron ionizes a gas molecule, which is then accelerated into the cathode. A second pumping action is accomplished by titanium sputtered from the cathode, which combines with gases to form stable compounds. Flat cathode and egg crate anode are typical in this design of getter ion pump. Capacities of several thousand liters per second and ultimate pressures of 10 to the -9 torr are achievable. Now let us turn to gauging. There are many methods of measuring high vacuum. The accepted standard gauge is the mercury McLeod gauge. It is made largely of glass, with capillary tubing for precision measurements and stopcocks for controlling the action. This one is set up to measure the vacuum in the alternating gradient synchrotron at Brookhaven National Laboratory. An auxiliary rotary type vacuum pump is used to raise and lower the mercury. A sample of the gas to be measured is admitted to the gauge. This sample will be trapped in the capillary tubing by the rising column of mercury. Since a sampling technique is used, it is not possible to obtain continuous readings with this type of gauge. Also, remote reading is difficult. In addition, the rising mercury will compress water vapor in the sealed capillary, condense it, and thus remove it from the sample. The McLeod gauge, therefore, does not indicate the pressure of vapor that may have been present in the sample. The advantage of the McLeod gauge is that it is the least variable of all gauges, since its reading depends on the physical dimensions of the tubing and the bulb, and these can be calculated and controlled. The stopcock will be closed when the mercury in the capillary tube at the right reaches the limit mark. If the gas sample, which is in the capillary at the left, is high vacuum, there will be few gas molecules in it, and the mercury will rise to a high point, indicating high vacuum. The most commonly used vacuum gauges are of the thermal response type, one of which is the thermocouple gauge. Inside a bulb connected to the vacuum system, a constant regulated current is passed through a wire. The temperature of this wire is accurately determined by a thermojunction affixed to it. If the pressure is low and a good vacuum is present, there will be few air molecules present and relatively few molecular collisions with the wire. The wire temperature, therefore, will be high, since little of the heat is extracted by molecular collision. Consequently, the meter will show good vacuum. But if the vacuum is poor, there will be more molecules and many collisions, lowering the temperature of the wire. This will be indicated by the response of the thermojunction. The thermocouple gauge is simple, convenient, inexpensive, and capable of operating remote equipment by relays from its thermally produced voltage. However, its range is limited to pressures between 1 torr and 10 to the minus 3 torr. For higher vacuum regions, ionization gauges are most widely used. They are commonly housed in glass tubes, but may also be made with a metal flange for permanent installation in a vacuum system. The gauge operates on a familiar principle. Electrons are emitted from a hot tungsten filament and are accelerated toward the grid. Some pass through and oscillate about the grid. During its flight, an electron may strike a molecule of gas in the tube. As a result, the molecule becomes ionized positively and is therefore accelerated toward the collector plate. The ion current falling on the plate is amplified and read as a signal proportional to the total number of molecules in the system. Cold cathode discharge, or alpha radiation, may be used as the ionizing source, but the basic principle is the same. Ionization gauges are capable of measuring pressures down to 10 to the minus 12 torr. We've come a long way from the days of Torricelli and von Guericke. Today, for example, we prepare and preserve blood plasma and various other biologicals and pharmaceuticals using the vacuum freeze-drying process for removing water without using heat. We take low-cost plastic shapes for jewelry and other ornaments and metal coat them under vacuum. The source of the coating metal is a wire, usually aluminum. Here it is woven spirally around a tungsten filament. The bottom of the bell jar has a sealing compound on it to prevent air leakage. The wire shield is a safeguard against possible implosion. The bell jar is now evacuated. When the pressure has been lowered to about 10 to the minus 5 torr, the filament is heated, causing the aluminum to vaporize. The surfaces of the plastic bracelet are thus coated with a thin layer of bright metal. Various color effects are obtained by vaporizing gold, copper, and other metals, or by tinting the lacquer that is applied to the finished product. Vacuum techniques are improving metallurgical processes by preventing oxidation and nitriding of molten metals. Steel plants today are melting, pouring, and casting, all at high vacuum. In controlled thermonuclear experiments, we are using ultra-high vacuum systems that work at pressures of 10 to the minus 9 torr and less. Yet this is but an inkling of the challenges and opportunities we face in this new technology. It may well be said that what we are doing today is but an introduction to high vacuum.